All right. Hello, everyone. My name is Igor Yusuf, and I am a founder and a software architect at Diligent Graphics. Today, I want to share some of the learnings from building our main product, the Diligent Engine. Diligent Engine is a modern cross-platform, low-level and graphics library, and it supports Windows, Linux, macOS, Android, iOS, and it implements Vulkan, D3D12, D3D11, OpenGL, and Metal backends. It is currently used in a number of production applications, ranging from games to pilot training systems to CAD application, industrial visualization tools, and others. It is open source and is available on GitHub under Apache 2 license. Here's what I would like to cover today. I will start with the motivation and give some quick overview of the API. The main topic I would like to cover today is the resource binding system. Of all the APIs that we support, I think that resource binding is actually the area that differs the most between all of them. And I think in Diligent, we managed to find a good balance between flexibility and the approach that supports all the APIs well. I will also talk a little bit about the offline state packaging tool that we implemented and about the testing. So if we try to arrange various graphics API on the flexibility versus the complexity chart, then Vulkan will be a clear winner. At the same time, it will also be the most complicated API to use. And for instance, if we use the number of lines in the Hello Triangle application as some measure, then there will be more than 1,000 lines of code in this application. DirectX 12 will be slightly less flexible and also maybe a little bit less verbose than Vulkan. On the other hand, OpenGL will be the least flexible API, but it is also will be the easiest API to use. DirectX is arguably provides the same functionality as OpenGL and maybe a little bit requires a little bit more code. Metal will be somewhere in between. And what we try to achieve with Diligent is to find the API that at the same time is as flexible, as powerful as DirectX as Vulkan, but at the same time is as easy to use as about DirectX 11. And even though Vulkan is usually been talked about as a graphics API, in reality it's not. What Vulkan really is a low-level API to control a massively parallel asynchronous processors. It is very hard to use for a graphics engineer that wants to work on a graphics problem to use Vulkan at least efficiently. And let's think about this from the graphics programmer point of view. Suppose we, as a graphics engineer, we just want to render a textured cube. And so to make this textured cube work in Vulkan, there are quite a few steps that we actually need to do. So, well, first of all, we need to, in our shader, we need to assign a non-conflicting descriptor set and descriptor and binding in the shader. Then we need to create a descriptor set layout that uses the exact same binding that we assigned in the shader. Then we need to create a pipeline descriptor that uses the set layout. We need to create a pipeline with this layout. Then we need to create a descriptor set from this set layout, and we need to write the descriptor at the binding in this descriptor set. And finally, we need to bind the descriptor set at the right index. And so there are a lot of moving pieces here, and it requires a lot of. If you want to do all this manually, right, it requires a lot of effort to make sure that all these pieces align very well. And I believe everyone had this problem where you say you have a mismatch between the descriptor set index or binding index that doesn't match your layout, and it creates all these issues that are hard to find, especially during development, right? Where you add and remove textures from your shader, and then you have to go, and on your host you need to make sure that all these indices are aligned very well. And the problem here is that all this manual work, it usually it hides the essence of the problem, which was just to bind the texture and to make it available to the shader. And one thing I want to emphasize here is that I'm not kind of criticizing that Vulkan is hard, right? I'm just trying to set the right expectation, right? That Vulkan is it serves the different purpose. It's not designed to be used as a graphics API, unlike, for instance, DirectX or DirectX 11 or OpenGL. And let's now just take a look at an example how this would work in Diligent Engine. So there are really just 3 steps. So we first create an object that is called a shader resource binding, and this object encompasses all the details, such as descriptor set and all the indices and all that. We then to set a variable to this shader resource binding object, we use a name, and we access this with this variable by name. And finally, we just call the commit shader resources command, which unfortunately you can't see because it's streaking out here. But we call just this command, and it binds all the descriptor sets and make sure that everything is at the Vulkan API level is properly handled. And yeah, so that's much easier. So this example that illustrates the main idea of Diligent Engine, to make an engine that is natural and easy to use, and that allows the graphics developer to concentrate on the problem. At this point, I would like to maybe clarify that even though it's called an engine, we are not trying to compete with like real engines like a game engine, especially like Unreal or Unity. We are trying to cover the area of graphics applications that don't really need the full-blown game engines, but at the same time they need an API that lets them solve their graphics challenges. So and one thing about Diligent is that we wanted to support all the modern features in Diligent Engine, like multi-threading, bindless resources, multiple command queues, ray tracing, mesh shaders, variable rate shading, sparse resources. So Diligent provides all these features, but through an API that is much easier and much more easier to use than Vulkan. And the other feature of Diligent Engine is that it provides flexibility. So it provides default implementations for many problems, like, for instance, resource synchronization or barriers. But at the same time, in the situations where the application can do better than automatic resource management, we let the application to take full control and drive. So let's now just take a look at some code. So in this snippet, we are starting to create a pipeline state, and it works similar to other APIs. So we prepare a create information struct that has basically all the same details as you may find in other APIs like Vulkan. So we set the number of render targets, the formats, the depth stencil format, primitive topology, and all that stuff. So nothing really extraordinary here. Here we are creating a shader, and shader creation is also flexible. It can be done in multiple ways. And a few details here is that, well, first of all, we provide a abstraction of the file system. So if shader compiler needs to access a file system, it can access this through a user-provided source factory. And Diligent supports multiple shading languages, HLSL, GLSL, metal shading language. It can also take compiled bytecode directly. And HLSL is the universal language. It's just a vanilla universe without vanilla HLSL without any extensions, without any special pragmas or whatever. And it works on all APIs and on all platforms. And yeah, so we create a shader and we set the shaders to the create infrastructure, again, kind of similar to other APIs. On this slide, we define the input layout, and again, nothing extraordinary here. It's just a two attribute vertex with 3 component position and 2 component textures. So this slide shows something a little bit more interesting. So it defines the shader resource layout, and the way it is done in Diligent is that every shader resource can be classified as one of the 3 types. We call them static, mutable, and dynamic. And again, the resources are identified by name, and the engine handles all the internal details under the hood. Here we show how the bindings are set. So as I said, there are 3 resource categories: the static, mutable, and dynamic. And static resources are set directly in the pipeline state object. So they are kind of the counterpart for mutable samplers that are baked into the pipeline. So in this, we can set a resource that the binding that never changes. We can set it directly in the pipeline state. The pipeline state creates the shader resource binding object, and the mutable and dynamic variables are set through this shader resource binding object. And again, they are accessed by name. On this slide, we set the render targets and clear them. And again, nothing extraordinary here except for the special parameter that every command that may require some state transitions, every command takes a special flag that tells the engine what to do in this case. And there are 3 options. So the engine can do no state transitions. It can automatically perform any required barriers or say layout transitions, or it can just verify them. And it's very important because in APIs like DirectX 11 or OpenGL, it was a major problem, especially for multi-threaded command recording, right? Because if you record commands in the synchronous thread, and then when you execute them in the main thread, right? The driver would need to go and patch and find if there are some states mismatches, and it would need to go and check all the states. And that was a major problem, and essentially which made multi-threading impossible in say DirectX 11, for instance, OpenGL. So in Diligent, we have this, we solve this through this special parameter, and for multi-threaded command recording, it is expected that the application will take over, that will control, and that will issue explicit barriers because it knows better how to handle such a situation. And finally, here we set all the required like vertex buffers, index buffers, pipeline state. We commit the shader resources, which again binds all the descriptor sets internally, and we issue the draw command. So let's now talk about more detailed look at the shader resource binding system. So I will first talk about the first version of this binding model that we implemented, and then we will build the second version on top of that. So as I so the engine uses the reflection to get the list of resources that are used by the pipeline state, and each resource can be classified by the application as static, and static resources can only be set directly in the pipeline state. The second type is mutable resource, and the mutable resources can be set in each instance of the shader resource binding object. And finally, the dynamic resources. Dynamic resources are different from mutable in a way that then they can be set multiple times in each instance of a shader resource binding object. And based on this classification, Diligent automatically assigns descriptor sets and bindings, and it patches SPIR-V bytecode in a way that it may so that it is consistent with the bindings that were assigned by the engine. Under the hood, each pipeline state may have two descriptor sets. One descriptor set for static and mutable resources, and the second descriptor set is for dynamic resources only. And the reason there are two descriptor sets is because dynamic resources are handled very differently, because they may be changed by the application freely. When a shader resource binding object that has dynamic resources is committed, the engine creates a copy of the descriptor set that has dynamic resources. It copies all the descriptors in this descriptor set and binds it to the command list. Within each set, there are three groups of resources, and which makes the total of 6 groups for the two descriptors. The first group is the uniform buffers that have dynamic offsets. The second, the dynamic offset storage buffers, and the last group is it contains all the other resources. And so this is the pseudocode for the function that assigns descriptor sets and that distributes resources between descriptor sets. So it goes through each resources that were identified by the shader reflection, and it uses the variable time that, as you remember, was defined by the application through the shader resource layout. So it uses this variable time to find the descriptor set ID. Again, 0 will be a descriptor set for static and mutable resources, and 1 will be for dynamic resources. It then uses the resource description to get the descriptor type, and that would be one of the many descriptor types in Vulkan. And finally, it finds the cache group for this resource, and there are 6 cache groups. And then it adds the resource using these properties of this resource. Then it updates the binding. Basically, it offsets it by 1, and it also updates the cache offsets. So to give an example, let's consider a shader that uses this set of resources. It has a global attributes, uniform buffers, some frame transforms, the mesh transforms, some special attributes, light storage buffer, and shadow map, and a few other textures. So the procedure goes through all the resources one by one, and the first one it finds would be the global attributes uniform buffer, which is a static resource with no dynamic offsets, and so it assigns it a binding 2 because there are because there are resources with dynamic offsets would be placed at the beginning. So the next resource it finds is the frame transforms uniform buffer, and it goes also into the first descriptor set and the binding 3 and cache offset 3. Then it finds the mesh transforms uniform buffer, which has dynamic offsets, and it goes into the binding 0 and offset 0. Then it finds the dynamic resource, and it places it into the second descriptor set, the descriptor set with index 1. Then we find light storage buffer and the shadow map, the base color, and the normals. And notice that since the base color and normals are arrays, we even they have the continuous bindings, but then the cache offsets will account for the array size, so that we have the space in the cache to keep this information. And the final will be the color correlation dynamic texture that goes into the descriptor set 1. So after we assign these descriptor sets and bindings, we need to patch the SPIRV bytecode to make it consistent. We use SPIRV cross to parse the SPIRV and get the offsets for the descriptor binding and descriptor set decorations. So when shader is loaded, we use the SPIRV cross to store these offsets. And when a pipeline is created, we use these stored offsets to patch the shaders. So basically, for every pipeline state, the process goes through all the shader stages, and in each shader stage, it goes through each shader. And in case of ray tracing, there may be multiple shaders in each shader stage. That's why there is this outermost loop. So the process goes through the list of shader resources, and it takes the binding and descriptor set from the resource layout, and it takes the decoration offsets from the reflection that was loaded when the shader was created, and it patches this SPIRV bytecode. So this is what the connection between different objects looks like. So there is a pipeline state that contains the layout object, and the layout object inside it contains this array of resources, and for each resource we have a binding and offset. And the shader resource binding object is just a cache of resources, so just a kind of an array, and with just the resource data. And the cache offset in the layout, it defines where in this cache where each resource resides. And for static resources, when a shader resource binding object is created, we copy resources from the static resource cache that is maintained by the pipeline state object to the shader resource binding object. Now, at runtime, to commit the resources, we first use the static mutable descriptor set from the shader resource binding object. And if there are also dynamic resources, we need to allocate a new descriptor set and copy all dynamic resources from the cache into this descriptor set. And if there are any dynamic offsets, we also need to collect them and write them. So this system worked well, but there were a few limitations that we wanted to fix. First of all, the problem was that the shader resource binding objects of different pipeline states were incompatible with each other. So the resources of one pipeline could only be used with another pipeline if two pipelines use the exact same resources. And also the problem was that all resources of every pipeline were consolidated. And for instance, we couldn't split the resources based on the frequency of change. For instance, like a frame-only resources, a pass resources, object-specific resources. And these problems were solved in our second version of the shader resource binding model that introduced an object that's called pipeline resource signature. And it's basically a counterpart for pipeline layout. And it defines the resource layout independent of any pipeline state. And each pipeline then may use up to 8 signatures, and descriptor sets and of each pipeline, they then stack on top of each other. And that makes the shader resource binding objects reusable between pipelines, and also it lets pipeline states to be bound at different frequencies. So this is how the pipeline resource signature is defined. It's similar to how shader the pipeline layout is defined, but also besides the variable time, we also need to define the resource type this time because the pipeline resource signatures are defined without having actual shaders. And so we define the shader stage, the name of the resource, array size, resource type, and the variable type. And so when a pipeline state is created, we now, instead of defining the resource layout, we now provide a list of pipeline resource signatures that this pipeline will be using. And so for each pipeline resource signature, the bindings and descriptor sets are assigned basically the same way as for as in binding model 1. And when pipeline is created, it goes when it needs to find a binding and descriptor set for each resource, it goes through all the list of pipeline resource signatures and finds this resource with the same name. And if the resource is not found in any of the signatures that are used by the pipeline, it's an error and the pipeline cannot be created. So this is what it looks like with a pipeline that uses multiple resource signatures. So each signature has a corresponding shader resource binding object, and each shader resource binding object contains a shader resource cache within it. And so here is another shader that uses resources grouped into 3 signatures. And if we assign it, if we look at how these resources are distributed between each signature, then the first signature will contain the frame constants and the sun shadow map resource texture. Signature 1 will contain the chimera transforms and ambient occlusion. And then signature 2 will have 2 descriptor sets that contain the static mutable resources. And the second set from this signature will contain just the dynamic light storage buffer. And so a pipeline state that uses all these 3 signatures, it will have the 4 descriptor sets. And these 4 descriptor sets, like I said, they will stack on top of each other. So with this model, we can commit the different resources at different frequencies. For instance, we can first commit just the frame-specific resources with the shader resource binding that only contains these resources. Then, if we have multiple passes, we can then commit first resources specific to each render pass. And finally, if we have a number of objects that use different pipelines and different shader resource binding, then we commit the object-specific resources just for this object. And Diligent Engine lets the resources defined in the code, but it also has the special language that's called Diligent Render State Notation. It's a JSON-based language that lets the shaders, resource signatures, and pipeline states to be defined outside of the program, so that they can then be compiled and packed into an object, into an archive object that allows the engine to load this all the states very fast at runtime. So the offline processing takes this JSON-based language and performs all the shader patching, the descriptor set distribution, and everything that is needed to make the pipelines work at runtime. This is what a DRSN looks like. It basically mirrors the API, but in a JSON-based language. Finally, I want to just talk a little bit about testing. We really care about stability and robustness of the engine, and we pay a lot of attention to testing. So there are a few ways we test we perform the continuous integration. First, we have the unit tests, And since Diligent supports multiple APIs, the way we use our unit, we implement our unit test is by having a reference implementation in each native API, and then we compare the results of native rendering with what Diligent generates. And this lets hide all the driver details and differences between different GPUs, because the reference is generated at runtime, and that lets us perform like a pixel exact comparison. This process intercepts any errors generated by, say, validation layers. If any errors happen, then the tests fail. And we run tests on each commit for on Linux. They run on Vulkan and OpenGL, and on Windows for Direct3D11 and D3D12. We also have a number of test applications and tutorials, which we also use for end-to-end testing, and that's mostly like a standard golden image validation, where if any change happens to the driver, we have to basically manually go and update the golden images. And so here are a few links related to the material that I covered today. So Diligent Engine is open source; everything can be used free of charge. And with that, I reached the end of my presentation. Thank you for your attention. If you have any questions, please, I'm happy to take them. All right, if there is no more question.
I have a question. How do you handle, because I actually know about your engine before, and I see that you can use it as a plugin. Like you can have it running side by side, correct?
Yeah, well, side by side, probably more like an inside.
Yeah. So how do you deal with OpenGL state?
So we have this, in the engine, there is a special call that basically tells the engine to clear all the internal states. So basically, when you switch from one engine to another, you have to basically tell the framework that it has to clear all the internal state tracking, and it can start it go from there, because how can you do this otherwise? We don't try to recover OpenGL state, for instance, using the queries. We just let this problem to be handled by the developer. Yeah, so the question was, do we track any resource states, and or is this up to developer to take care of this? So it's we can do both. So let me show you this slide. Where is my lots of geez. So that's right side. So it can do both. So it can handle the resource states, all the barriers automatically. But if the application knows how to do better, it lets the application issue manual state transitions and everything. And like in cases like multi-threading, that's expected of the application. That, for instance, if an application doing multi-threading, probably doing something like a frame graph, so it already knows what barriers or what states need to be issued. And in this case, the application may disable. It may tell the engine that the application now takes full control over the states, and the engine will do nothing in this case. In the majority of situations, like especially if you start an application, you probably don't want to you probably don't need or don't want to care that much about the states, and the engine can handle this for you in this case. So what are the limitations? So from the graphics point of view, I would say our biggest limitation right now that we want to fix at some point is multi-GPU support. At this point, we support all the major features: ray tracing, mesh shader, variable rate shading, sparse resources. Well, of course, things like MSIA and all that. It's obviously everything is supported. So yeah, I mean, we are trying to be on par with the advances in API development, but we clearly lag a little bit behind. But the engine also lets you do the interoperability with the native API. So, for instance, if there is something in the most recent Vulkan API that's not in the engine yet, you can just go and switch to native Vulkan, and so for this specific part, you can do just Vulkan. You don't have to write everything to use Vulkan. For instance, you can I don't know. You want to use I don't know, some new extension that is not yet available. Then for that you can query from the engine the command buffer, some states like native texture handles, and you can write your own native code. So yeah, we tried it to make flexible in a way that if something is not there yet, you can. There are other ways in which you can achieve your goals without without having to basically write your own framework from scratch. Yeah, please.
You can measure performance between different native APIs in your engine, or for example, your Dave's implementation has the same CPU overhead as Vulkan implementation. If we talk about resource handling system.
So the question was about the performance, how it compares to native implementation. So the framework definitely introduces some overhead. It depends. It differs between the APIs because, like DirectX and Vulkan, for instance, they have bottlenecks in different places. For instance, we have some performance tests and benchmarks for that. And the bottleneck is really in different places. For instance, in Vulkan, the pipeline state change is very expensive code. For instance, and while for DirectX 11, for instance, mapping a buffer is very expensive. While in our Vulkan implementation, mapping a dynamic buffer is essentially like no op. So. In our tests, I would say we introduce in super CPU heavy applications, we introduce maybe like 20% overhead above the native. But again, there are multiple ways to make it more performant. We have we were trying to make it really explicit API so that you can provide a framework special hints that help it do better. For instance, if you your shader uses dynamic buffers, and the engine by default has to check if you actually mapped this dynamic buffer and if the if you wrote if you updated the content. But if you know that you haven't actually mapped any buffer and that you haven't updated it, you can tell the engine that nothing has changed, and it will help save it some performance. All right, I'm sorry, I think I'm out of time, but I will be here after that, so please get back to me. Yeah. Thank you very much.